Hi everybody, today we're going to talk about graphing data. You all know in science that there's a lot of different ways to present the information that we have via experiments or through our problem solving. We can use words, we can use pictures, we can use equations, but one of the simplest ways to present information that is clear and easy to read is through a graph. So the objectives for this lesson are to graph the relationships between variables. We do some measurements in class in an activity or an experiment. We want to be able to observe the relationship or portray the relationship between variables in that experiment. So we're actually going to make some graphs. I know that some of you probably have used graphing tools like Excel, but we'll actually be doing quite a few in class by hand, just to make sure that we really understand what's going on and what information we can convey and get out of graphs. Next, we want to be able to interpret graphs. So that means we want to be able to read information from the graph. We want to be able to get values off the graph. We want to be able to extrapolate and get values that are probably maybe not on a graph. Come up with equations for a graph. And last but not least, even just determine the relationship between our two variables from the graph type we have. And then by doing so, we can do our third to recognize some common relationships in graphs. Are the two variables related linearly, or is it a quadratic? How does one variable change with respect to the other? Okay, so we all know that we collect data during experiments, and graphs are useful for us because, as we said, we can use those graphs to determine trends in the data, make predictions about data, but most importantly, we can usually use it as a simple and very visual way to support or disprove our hypotheses about our experiment. What question are we trying to answer? And does the data support the hypotheses or the answer that we thought it would? A couple different ways to present data in graphs. You're probably all familiar with those pie charts, bar charts, and the last but not least are these scatter plots sort of over here that you're used to with the X and Y coordinates. They're mostly what we're going to be using in class. We'll be using those scatter plots where you go out and you plot your data as a coordinate point on a plane, and you go ahead and try and figure out the trend from the resulting curve that is formed. You can remember, when we take our data in our experiment, we want to have a controlled experiment. We're usually trying to look to see if there is a relationship between two variables. So we control one or manipulate that one and then observe a change in another variable. If we didn't have just one variable controlled and that we manipulated, and if we let too many variables change, we really wouldn't know which variable was causing whatever change we observed. So when we do have a controlled experiment, that means that we have to have one variable that we control or manipulate, one variable that we observe to see if there's any change as a result of manipulating that controlled variable, and all the other variables have to stay constant. There can't be any changes with those. Otherwise, we don't know whether or not the manipulated variable actually caused the change that we observed. So if you look at something like this experiment here, the students doing a chemical reaction and collecting the gas, so they are controlling when they observe the change in the volume of gas. So they're controlling the time. That is their controlled or manipulated variable. And the one that they're observing a change in is the volume of gas. So when you graph data, you want to make sure that your relationship is clearly portrayed. You want to make it easy for your reader to understand what's going on. So you want to follow some good rules. The first thing you want to know is what your variables are. So in a controlled experiment, the variable that changes, that you manipulate, is called the independent variable. That's the one I'm going to change to see if it produces a change in some other variable. The variable that responds to changes in the independent variable is called the dependent variable. Some people call the independent variable the manipulated variable and the dependent variable the observed or the responding variable. But you just want to make sure that you realize that the independent one is the one that I control. I make the changes, or I say when I'm going to measure something in my responding variable. Okay, when you want to portray that data, you then have to really do it in a good graph. So there are generally just a few steps to be able to make a good graph. The first is to make sure you know which of your variables is the independent variable and which is the dependent variable. The dependent variable always goes on the y-axis, the vertical axis in your coordinate system, and the independent variable always goes on the x-axis, the horizontal axis in your coordinate system. Once you know which one goes on which axes, you want to make sure that you label the axes with a title, meaning what is the measurement that's going on there, and bring its units along too. You have to let your reader know what units your measurement is in that you are putting on your graph. And last but not least, you want to make sure that you give your graph itself a title. In this case, you can see this one is volume measured over time. It's always appropriate to title your graph in the format of y versus x. So whatever is your dependent variable on your y-axis, it's versus your independent variable, which goes on your x-axis. If you think about it, what you're trying to do here is see if y is a function of x. If you remember from math class when you maybe talked about functions, that's what you're trying to see here. So if you remember how that forms, we're just trying to see, is there a relationship? Does y change because my x changes? All right, your next step is to make a good scale for those axes so that you can start plotting your points. Now, usually you want to use as much of your graph paper as you can. You want to get that graph, all your points, as spread out as possible over the area of your graph paper. And you do that by figuring out your range of values for each axis. How many numbers do I have to cover? So for example, in this one I had to go from 0 to 180 seconds for the time, or I had to go from 0 to 180 milliliters for my volume of my gas. You want to know how high you have to go in your numbers so that you can fit all your data on your graph without squishing it in one particular corner. When you do that, you then have to say, okay, what's a reasonable interval to break up that range? Usually I would recommend that you count your multiples for your intervals by ones or twos or fives or tens, maybe even fours. Sometimes we're tempted to do 3, but you want to try and get it so that each block represents a fixed number. So even if that fixed number has a 0.5 or a 0.25 in it, that's fine if you're doing the multiples of, say, 2 or 4. But if you do it in multiples of 3, what happens is each block ends up being 1/3 of something. And hopefully you remember that 1/3 is not a definite number. It just keeps going on. And it makes it sometimes difficult then to plot our points or read our points well if they're in those multiples of 3. Point you have to remember is the scales do not have to have the same axes, the same scales on the axes. So as a result, you can scale 1, meaning it is, for example, the time in this one could have been every block was 10 seconds, but every block of volume was 20 milliliters. The scale doesn't have to be the same. You just have to be consistent on each axis. And last but not least, you also don't have to include the origin. If the origin is a point or close to a point, at 0, 0, that's great to have. But if your data is really high, your numbers are very large, you might choose not to have the origin, the point 0, 0, as the intersection of your axes. But just if you do that, please make sure that the axes are scaled consistently from whatever you make your origin point be. All right, so now you come out and you plot each point. Simply go out to your x and your y coordinate and plot your point. Remember, points always go in the form of x, y, so that means you're always going to be plotting your point with your independent value and then your dependent value. And you want to make sure that those points are clear and where they are is as close as possible as where they can be. You might even want to look around and put your point and then put a little circle or something around it just to indicate a little bit of that error around there, but to also give you a good idea of where exactly the point is. All right, your last step then is to try and determine the trend, and you do that by drawing a small curve that shows the pattern of the points. You don't just connect the dots, so you don't do a zigzag through, but you create a smooth curve. Generally, in class, most of our relationships are going to be linear. And if not, we're going to linearize our data so that they can be linear. And when that happens, you draw a best fit line, meaning you draw a line through as many points as possible, as many of your data points as you possibly can get through. And then once you have that, you want to make sure that that line, though, isn't skewed. So any of the points that are not on the line, you want to make sure are evenly distributed on both sides of the line. If you put a line too high, where all the points that are not on the line are all below it, or you put a line too low, where all the points that are not on it are above it, you're skewing your data. So you want to go sort of right up through the middle of the points in order to get your best fit line. We'll do some practice with that in class. All right, once you have a good graph, or if someone has provided you a good graph, one of the great things is you can also now read data from that graph. You can make predictions of values for maybe values that you did not collect data for in your experiment. So you can see here someone was doing position and speed at certain times. So they only had data for the points of the position at 20 centimeters, 40 centimeters, 60 centimeters, and 80 centimeters. But now using their graph, they can actually read the information as to what the speed would be at 50 centimeters. You simply go up from your X value, find where that intersects your curve, and then go back to the Y-axis and get its coordinating point. So you can come up with an X and Y coordinate for that point on the line or the graph. Right? A lot of what we're going to work in, as I said, will be linear relationships. So we want to make sure we can look at the relationship, and we determine linear relationships generally by the slope of the line. And if you remember, that means the steepness of the line, how quickly the dependent variable changes with respect to the independent variable. And if you look at it, you sort of visualize, if you know your slope formula of the difference in your two y points divided by the difference in your two x points, that's great. But you can also remember your typical rise over run, where you visualize those 2 points as your slope triangle, where the rise is the change in the height of that triangle, where it's the difference in the y coordinates, and the run is the difference in the x coordinates. Remember that if, as you run along the x-axis, you're going up the hill, your slope is positive, and as you run along the x-axis, if you roll down the hill, your slope is negative. So here's where you would go and be able to determine that relationship. You just simply take the rise over the run, and it comes out with a number. It gives you that relationship. The bigger the number, the steeper the line is going to be. The smaller the number, the shallower the line is going to be. But what I want to really point out with this is slope. A lot of us just think that slope is a number. But when we start looking at graphs in class, slope is that relationship between those two variables. Those variables have measurements. So as a result, you can see here that the slope not only takes the rise and the run numerically, but it brings the units that are on the rise and the run axes. And those units actually turn out to be part of the ratio for your slope. So you see units are important, they come along with it. So if you look at something like this, position over time is giving us actually units of speed. So we can see how fast we are changing our position with time. So units coming along with your slope are very important. Make sure you pay attention to them. And last but not least, some of the common relationships that we might encounter. We have direct linear relationships. All right, so one variable goes up, the other variable goes up. You have inverse relationships, whereas one goes up, the other one goes down, and generally those are not linear. If we do have those in class, we probably will do some linearizing because it helps us to actually see the graph as a line. But you just want to remember, if it's a direct relationship, it's usually a line is what we would say, and that is one variable goes up, the other one goes up. If one variable goes down, the other one goes down. Is when we talk about they do the same thing. When we talk about an inverse relationship is when we talk about as one variable goes up, the other one goes down. So they do the opposite things. So these are some of the common ones that we'll see in class. I don't think that we'll see all that much different. We might occasionally see a quadratic or something where we see a rate of growth with a power or an exponent. But generally, we should be working mostly with lines.